Hi, my name is Nora Lützgendorf and I'm an astronomer at the European Space Agency. Today I want to talk about light and the electromagnetic spectrum. First of all, what is light? Light, or visible light, is just one part of electromagnetic radiation. This kind of radiation can be seen as a wave, similar to the wave that you see when you throw in a stone in a lake, or a very fast particle that moves with the speed of light. But for today, we're just going to be talking about the wave character. So visible light is everything you see around you. It comes from the light inside your house or the light from the sun. You sometimes even see it split up in its components, the different colors, when you look at a rainbow. Our eyes are only equipped to see visible light, but there is actually so much more to the electromagnetic spectrum than this. Let's take the wavelength of the visible light, for example. This wavelength is in the order of 100 nanometers. This is as big as the point of a needle or maybe a single-cell organism. If you make that wavelength even smaller, to the size of a molecule, you get what we call ultraviolet light. You cannot see that light, but it would probably look very violet. It is the light that actually produces vitamin D in our skin and makes our skin tan. It comes from the sun, but again, we cannot see it. Now making this wavelength even smaller, to the size of an atom, then we get what we call X-ray radiation. You have seen this before in your doctor's office, because X-ray radiation can actually go through our skin and reveal our bones. Making it even smaller than this, so 100 times smaller than an atom, to make it to the size of the core of an atom, you will get gamma ray radiation. Gamma ray radiation is very energetic radiation, which we don't see very often on Earth, but we have seen it in the universe. Very big events such as supermassive black holes merging can produce gamma ray radiation. Now let's go to the other side of the spectrum. Let's make the wavelength bigger. If we make it as big as a blood cell, or maybe even the thickness of a hair, we get what we call infrared radiation. Infrared radiation is also called heat radiation. You might have seen it when you look at the heat camera and you see which body parts are hot and which are cold. All bodies in the universe actually emit heat radiation. It doesn't matter if they're cold or hot. And we cannot see this radiation either, but sometimes we can feel it. Making it bigger, to the size of an insect, going from 3 millimeters to 30 centimeters, we are coming into the regime of the microwave radiation. You have something like this in your own kitchen. A microwave uses microwave radiation to heat up water. Making it bigger than this, going to the biggest wavelengths that we have in the electromagnetic spectrum, going to 100 meters and bigger, it's what we call radio radiation. Those are such long wavelengths that they are able to travel very, very far and undisturbed. And that's why we use this a lot for communication. Radio radiation can be transmitted and also received from those really big radio dishes that you often see. Now you have seen that light is only one small part of the electromagnetic spectrum. So if we observe the universe only in the visible light, we wouldn't see much. We would only see a very small part of the universe. Luckily, we have developed instruments and telescopes that can observe the universe in different wavelengths. Those different parts of the electromagnetic spectrum reveal different parts of the universe. Take infrared, for example. Because of the size of the wavelength of the visible light, which is about the same size as the dust particles in our universe, visible light cannot go through dust because it will be absorbed and scattered by those dust particles. However, if you have longer wavelengths, such as the infrared, they can go through dust unnoticed. This is the reason why telescopes that observe in the visible, such as the Hubble Space Telescope, gave us those amazing images. But whenever you observe a dust lane, you would see just a dark spot on the image. Telescopes that observe in the infrared, such as this James Webb Space Telescope, will be able to look what's behind this dust. This is really important for objects such as supermassive black holes in the centers of galaxies, because they sit behind big dust lanes, but also for the birthplaces of stars and planets who sit in dust and gas clouds that they were formed of. Out in space, away from the hot and busy Earth, the James Webb Space Telescope will be able to observe a whole new world for astronomers in the infrared. you.